Thank you everyone for coming. Today we have Gaspar Fuster, which is doing his master in bioinformatics and biostatistics at work, and today he's going to present his master thesis. And he has been working at the data lab this past month doing his internship. So let's see how it goes.
Thank you. Okay, thank you very much for that, and thank you for coming here. As Roberto said, I am Gaspar Fuster, and today I am presenting my master's thesis, which is titled Object Detection of the Invasive Species Opuntia ficus-indica from Google Street View Imagery. Okay, first allow me to present the project. My work is part of the project Street View Sentinel. It is conceived by Erola Fenoyosa, who is my supervisor, and is founded by the British Ecological Society. Okay, now a little bit of context for this work. As we all know, invasive species are a growing economic and ecological problem. And traditional monitoring methods often rely on survey fields, which are costly and hard to scale in time and in space. And recent advances in deep learning show that applying deep learning for monitoring invasive species, they are acquiring very good results. Okay, that's why we focus on Google Street View as an ecological dataset. I don't know if you are familiarized with Google Street View. Here there is a video to show what it is, in case you don't know. But well, it's one of the largest public data source of street level imagery that not only offers large coverture, but also different moments in time. As we can see here, we have photographies for different moments in time. So we think that this dataset contains a lot of values ecological information, and the problem here is how we extract this ecological information. Okay. The state of the art on this matter is, on the one hand, as I said, deep learning approaches are currently showing very good results in monitoring invasive species. And on the other hand, this author, Kotowska, that's a figure from his article in 2020, first explored Google Street View as an ecological dataset to monitor invasive species. He manually did 50 transects of 500 meters, monitoring to invasive species. And here we propose to optimize this approach by applying deep learning with Google Street View. Okay, to address this problem, we have downloaded. Okay, first, why we chose these species to address this problem? First, Opuntia ficus-indica, I'll introduce this species, is a succulent species belonging to the Cactaceae family. It's native to Mexico, and now it's widely spread through the Mediterranean basin. Okay, and we chose this species because its morphological characteristics are highly distinctive, which allow an object detection model to easily learn these morphological features. Okay, then the study area is Sicily. We downloaded, as I will say now, 16,000 images from Google Street View on this area, on this island. We chose Sicily because it has an extensive and consistent Google Street View coverage, and because of the abundance of this species in Sicily, according to data from the GBIF. Okay, the dataset consists, as I said, of 16,000 images, and there are 360 degrees images, very large. We have around 8,000 pixel height and 16,000 pixels width. So they are very large images. What is a challenge to train an object detection model on this data? Okay, from these 16,000 images, around 20% of them were manually annotated, drawing bounding boxes around the species. In total, 3,151. Okay, from these annotated images, only 619 contain at least one Opuntia. That is another challenge to train an object detection model, because it's a really limited data set for a deep learning approach. But we have a lot of instances in these 600 images, because we have around 5,000 total individuals. The histogram shows that the major part of these images contain few Opuntias, with some images containing a lot of instances. Okay, I will also describe the bounding box area, because I want to show you that there is a big size imbalance in the area of the bounding box. If we compare the maximum in these images is a very big individual compared with the minimum size that we barely can see the objects here. I don't know if you appreciate it in red boxes, but there are also Opuntia. So that's the other challenge of this project. And while the standard deviation further confirms this size imbalance. Okay, to address these three challenges, the size imbalance, the limited size of the dataset, and the huge images, we have run 3 experiments. We trained an object detection model with the architecture of YOLO, and we did 3 different preprocessing strategies. First, I will show you a visual example in the next slide. First, we have the raw dataset, which is just a control version to see how it changed the other approaches. The window dataset, what we did is to split the image into halves and then crop non-informative regions. I will show you now, with the objective of reducing the image dimension. Then we did what I call the tile dataset, which is a centered-based tiling. We crop a square part of the image where we had annotated objects. That way, we reduce the image dimension. We also augment the effective size of the dataset, because we do 2 tiles per object. So if we had 5,000 objects, then we will have 10,000 images. And we also increase the relative size of the bounding box, because it occupies a major part of the image, the bounding box. So we try to solve a little bit the problem of the size imbalance. Okay, that's a raw image, like the one we saw previously. Then this is the window dataset, splitting the image in 2 halves, and as we can see, the sky is a non-informative region. We can find the plant there, the road too, and then cropping the distant vanishing points, we will filter some really small objects. Then we have the tile dataset, is the same images, focusing on these 3 boxes. I don't know if you can appreciate it. We do a tile centered in each object. So that way we have images with less dimension, more data set. And what can happen here is that when cropping bounding box, we create these really small bounding box that has no information. These boxes were filtered, and by doing this, we also remove some really small objects, like the one we saw in the minimum area. Okay, so training a model with these three preprocessing strategies, we obtain the following results, which are interesting, because here I plotted the evolution of the training loss and the validation loss, and although these results looks really bad, I can explain later. We will see. Well, what happens here is we can clearly see overfitting, because the training loss keeps decreasing till the end of the training, which means it is memorizing the exact position of the bounding boxes. And when try to generalize this to unseen images in validation data, the loss stabilizes in early epochs. Okay, and then the question here is why haven't we stopped the training in epoch 20? Okay, because we track other metrics like precision, recall, map 50, and F1 score. And these metrics, in the tile data set, which is the pink line, we see how these metrics still improving almost till the end of the training, because the model, although it do not locate perfectly the plant, it is still learning useful features to identify what is an Opuntia and what is not an Opuntia. Okay, to try to explain this contradiction between this metric, the bounding box loss, and these other metrics, okay, I draw these blue boxes, what represent possible predictions of the model. What happens here is that the intersection over union, which is measured with this formula, measures how well the predicted box is compared to the ground truth. And what we see is that the model do not learn how to differentiate different individual plants, which is closely related with the fact that this plant has a clonal growth and often creates these clustered areas, which even for us and for experts is very difficult to say, okay, that's an individual and that's another individual. The annotation process was made by experts in this plant, and with his expertise and human context, tried to say, here starts an individual and here starts another individual. But obviously the model do not learn this. But the other metrics which are based on, okay, you have identified that number of plants. If we consider that imagine this is the ground truth and this is the predicted box, if we consider this as a true positive that has correctly located an Opuntia here, those metrics are still improving, because although it not correspond perfectly with the ground truth, it's still identifying the plant. And here I have I show you a real example of prediction with a tile model that identified plant where there is an Opuntia, but for example here the annotation would be here one, another, and maybe here we have four real Opuntias, but the model says, hey, there is Opuntia, and that's quite well for us. I will show you now. Okay, as an object detection model, is not a really good object detection model, but we can further improve that by one, a good inference strategy, and then adapting the model. First, the inference strategy consists in two parts. First of all, we create the window preprocessing in all the images. That way, we remove those parts where we can possibly detect false positives. Obviously, there won't be any plants in this region and also in this region. And then we apply inference using SAHI, that is a sliced prediction. I will put the video again. Okay, this is an example from Ultralytics, just to show you how does it works. It makes small predictions, and that allows the model to focus on smaller instances. Then we have adapted the model, the object detection model, to a classification model, because it is not really necessary the information of exactly where do we have this invasive plant. Just by knowing, hey, in these coordinates we have Opuntia, there is presence or absence, that's also useful. And to adapt this model, we use a simple rule. If we detect at least one plant, there is presence. If we don't detect any plant, there is absence. I mean, there is not the plant. Okay, by doing this, I constructed this confusion matrix on unseen images. This is new images never seen by the model, and and we use the confidence threshold of 0.65. So we achieved these metrics that are really good for a classification model, and 93% of the predictions are correct, which is a good metric to now apply this model to real life. Well, here there is a question: why haven't we trained directly a classification model? And first, because the data set was already annotated when I started the work, and then because classification model, binary classification, has one problem. That is, we have two classes, which is Opuntia and not Opuntia. Okay, Opuntia, the model learns what is an Opuntia, but by learning what is not an Opuntia, the model has to learn everything that is not Opuntia. So it's a very ambiguous class. So it has to learn that a car is not an Opuntia, a tree is not an Opuntia, the road is not an Opuntia. So there is too many things that can be an Opuntia. So classification, an object detection model, it works also as a classification, because first it locates a possible region where we can find a plant, and then it says, is it or is it not a plant? So that approach works well for bigger images where the Opuntia can be in a small region of the image. Okay, then with all the 16,000 downloaded images, I ran all the prediction using the previous inference strategy, and adapting the model as a classification. So all those green points represent a simple image where we have presence of the Opuntia. So and also with these points, I've created a kernel density estimation, so we can see a little bit the spatial distribution of these species. Now it's interesting to compare this approach, our approach, to other ways to create distribution maps. The standard way to create a distribution map for ecological studies is to get data from published data source, such as GBIF, a Global Biodiversity Information Facility. If we go to GBIF and we download all the dataset first, we obtain that we have 379 examples of Opuntia in all the island. and then creating a map with this data, we obtain these spatial distribution maps. We see a hotspot here, but some authors already has highlighted that in public data source there are a bias, which is a sampling effort bias, because if there is some specific campaign in a specific zone of the island, then we have some area which is overrepresented. Comparing this to our map, first, we have seen 4,000 images with presence of Opuntia, and we know that if there is one Opuntia, most likely there is more Opuntia. So just we have 4,000 images with presence of Opuntia, and also the hotspots do not correspond with the map created with GBIF data. I'm not saying that this approach have to displace other methods, but they are very complementary, because whereas my approach offers large scale coverture, other approach can provide data where there is no roads, for example, or there is no, areas where are not visible from the road. But we have to interpret this map as what it is a map created just with information from the road. We can interpret that as a perfect distribution map, but it's a really good approach because it provides a lot of data. Okay, and well, finally, I wanted to show you this tool that I created. I uploaded all the predictions in Google Map, and then we can activate the street view layer, and we can manually go and see, okay, is there Opuntia here? And we see, yes, that's Opuntia. We have here Opuntia as well. And we have more Opuntia. So the model in 93% of the cases is sure that it will find this plant. Okay, and just to sum up and to say the main idea of this project is that combining deep learning with Google Street View is a really good approach to obtain distribution maps. And just, yeah, the idea is that Google Street View has a lot of various ecological data, and with deep learning, we can extract this data. And of course, there is a lot of future work to do in this project. For example, we could quantify the invasion risk by applying land use map, for example, and see, okay, there's a plant, but it's in a urban area. Okay, that's not, there is no invasion risk here. Or we could also try to manage the uncertainty of this prediction, because here we do it manually, as we seen before, by going to the layer of Street View and see is or is not, is there or is not Opuntia there. So try to apply some model to quantify this uncertainty. But well, there's a lot of work to do, but I think that these results proves that using Google Street View as an ecological data can have really good results. So well, here's the bibliography that I've used for this presentation. And if you have any question, I will be pleased to try to answer it.
I'm not sure, when you choose the 3 ways of using the dataset.
The preprocessing?
Yeah.
Yeah.
So at the end, are you able to take the ones that are so long and so small, or you?
To predict those?
Yeah.
Okay, you mean here in the tile dataset, I said that we filter out really small bounding bots. such as these ones.
Yeah,
Okay, these really small objects.
you don't take into account.
No, we don't take into account because they are really far and really small. But the model in this, by using SAGI as slice prediction, it focuses on small objects, and we can identify these
Yeah,
examples which are really
and
small.
you use Saki, and so, but you, in your ground truth, the last one is not inside.
Yes.
So it really is the species
Yes.
that you're telling in the ground truth that it's not.
Yes, I realized it this when training the model. I said, okay, this is just giving information that is not really useful because it's very difficult to learn that is the same thing that this. But when I run the inference, I realized that the model really was identifying those small examples. So a future, I mean, the model is not the final one, and training it with small instances, or maybe another approach could be
Well, you can-
use two classes,
Yeah, you should
big
use,
and small. Yeah.
yeah, that's
that's
really
interesting.
profile. Because
Yes.
maybe you're interested only in the big ones, but for sure it's not to look at the small ones, so.
Yes, what I wanted to do by filtering small object is to create a deliberate bias towards larger plans. That way, if we detect this, we are sure that this will be an Opuntia because it's really big. But yeah, I didn't expect the model to predict really small objects.
Yeah.
So that would be a really future step.
Very amazing work. I just have a slide. I don't work with this, but then the cropping, you also, like, you do it or the model does it?
Which cropping?
Like the first cropping where you take out the sky.
I know I did manually with code. I say first I crop this and then I train the model with these cropped images. The model does not do it.
Okay.
We do it previously.
And then you also have to select manually some Opuntia.
No, it's proportional. So I said 30% of the top region removed, and I did some tries with different images to see if I am not cropping informative regions, and by doing some tries, I selected the best proportions.
And then you had at some point also, when you already had the crops, to select manually the Opuntias, right? And then by
No.
selecting you, then you train the model.
No, I mean the annotation was made with these images.
Oh.
And then I cropped here, and if I crop some object, the object also crops. So the annotation is previous to the cropping.
And are you using the bounding boxes for? I mean, and are you planning to use the bounding boxes in some way to have disadvantage to maybe quantify
The total number of plants, you mean?
No, not that, because I think this is very difficult because there are many plants together, so I think to count, but to quantify the uncertainty, maybe to say, well, for example, you have put one of the images that appear later, when you have when you have many plants.
Okay.
This one, for example, not the one. This one, for example, here you are very sure that there is an Opuntia because you have many boxes, very big boxes.
Yes.
So maybe you can use the boxes to quantify the present absence in this image.
You mean
maybe you have if you only had this last one, the Opuntia of 0.51
Yes,
in that image,
Okay.
maybe yeah, there is a present, but the confidence would be lower
yes.
than when you have the rest.
Yes, there is a, well, processing work with all the predictions in the test data. And we can filter by, I just have filtered by the confidence. Well, I filter by the confidence threshold of 0.65, which reduce the number of false positives. And yes, we also could have filtered by if there is instead of using this rule, at least one detection, we could use some more elaborated rule. For example, if there is at least 2 detections with a higher confidence threshold, for sure that will improve this confusion matrix.
Because this one, you are saying that if you get like one result, one box with more than 0.65, you consider it
Yes,
as
as a
detected.
positive.
But if you had like 6 detections, but with 0.5, you won't consider it.
That's a false, yes. I
But-
will consider that a false, yeah, false positive.
But maybe if you have 6 annotations, maybe
Yes,
for example, in the previous image that you have 0.51 and you have some plants in the background, you in this part you do already have some plants, but you are not detecting. You are saying like this.
oh, yes,
area.
we are losing some plans because of this confidence threshold. But what I've seen is that the plants which are really Opuntia has higher confidence threshold than that ones who are not really Opuntias. They have a lower confidence threshold. So I haven't checked this if there are a lot of predictions with lower confidence threshold. I will do it
Because the prediction you put there
which one?
is using Sahi, the one that you have many plants and the other one in the background. The one before that we were talking.
Okay.
You
Okay, this one
this one,
or this one.
this one.
Okay.
You apply Sahi here also?
Yes,
Okay.
we first do the preprocessing window. That's a window. I mean, that's not the whole image. That's just a window. And then in the window, we do the Sahi. Yes.
Congratulations.
Thank you.
First. Have you or could you, in the model, like identify also like potential consistently other objects that are consistently being identified as Opuntia but are not?
Okay. Well, one thing that the model used to confirm is viña. I don't know, sorry, I don't know why it's not similar, but if the model identify it as an Opuntia. And another thing that is important to highlight is that when applying this model to other regions where there is more Opuntia species rather than Opuntia ficus-indica, the model for sure will detect other Opuntia species. Because here in Sicily, the dominant Opuntia species is this one, and that's why the model is sure that it's an Opuntia ficus-indica, because we know that it's the dominant Opuntia species there. But when applying this model to other regions, it will detect other Opuntia species. So it will work as an object detection of the Opuntia gender more than the Opuntia species. but there are random false positives. I mean, in one case, it detected a graffiti would have similar shapes and the viña and
Yeah, I was
other
curious if
plants.
there was like a consistent mistake that it was making with some other thing that is also maybe often
Yes,
found.
mainly the viña.
Yeah.
So you should introduce as a class.
Yes.
We're going to improve our-
Yes.
And you could also introduce images of this species, but images from.
Yeah, small event, yes.
Like random images that you get from internet.
Yes, in fact, the future step of this project is to extract data from web scraping, Google, and download maybe, I don't know, 200 images. The first 200 images when we search Opuntia ficus-indica habitat, and use this also with this data.
Yeah.
So the model will learn more accurately what is really in Opuntia.
No questions for Gaspar? No, you can leave it. Thank you very much.